Good evening, everyone. So we will now look at the last part of our course module, which is basically the design of control systems using frequency response. So just to recap, we were looking at what is frequency response in the initial part of this chapter. Okay, we learned that frequency response is an alternate way to look at process characteristics, considering that inputs and outputs are based on signals. Okay, so the key aspect here is frequency, which essentially means that you will have to move from the well-known Laplace domain to the frequency domain. Okay, which is generally achieved by substituting s equal to j omega and rationalizing the transfer functions. And there is some well-known relationship between the time domain, frequency domain, and the Laplace domain. So all are equivalent, and these transformations are also quite generic. So later we have looked at how to represent frequency domain characteristics. So one classic way is to look at Bode plots. You would see which is a function of mostly omega tau, which is a function of omega, of course, and the amplitude and the phase angle, which is obtained by rationalizing the complex function. And we looked at various Bode plots for various systems, for instance, first order, integrating system, second order, time delay, and various controllers, PI, and things like that. So another aspect of Bode plot is that it is not really handy. So it contains two plots. One is a function of amplitude, and one is a function of phase angle with respect to the omega, which is the frequency. So Nyquist diagram is a compact representation of all of this. Here we will not have two separate plots, but instead you have a single compact plot, which is the polar plot, which essentially means that the amplitude ratio become the radius from the center, and phase angle become the point wherein you mark that point. So for instance, this is a first order system. If you look at the phase angle is 0, amplitude ratio is equal, so the point would be right at the diameter 1. Then it would eventually shrink, and when you look at omega become infinity, your amplitude ratio become 4. So even the phase angle is minus 90. So minus 90. So this is the way you compute the angle. So this is 0. This may be minus 90. And amplitude ratio is equal to 0. And any point in between would form the curve. Then you can calculate and plot it. So now what we are going to look at is Bode stability criteria and how it is used to repress or used to characterize the stability of the system. It is slightly better compared to Roche stability, considering the fact that the time delay issue, wherein you will have to convert your transfer functions to polynomial, is not there in context of Bode, because it would take that things automatically, because it is just based on amplitude and frequency, and for amplitude and frequency you have a well-known way to characterize even if you have exponential time delay. So your amplitude ratio is just become 1 and phase angle become minus omega theta. So before we look at Bode plot, of course this is the characteristic equation, and that would give rise to open loop transfer function is equal to minus 1. So we would look at two critical conditions, which is called amplitude ratio is equal to 1, which essentially means that the modulus of the open loop transfer function is equal to 1, and the phase angle or phase lag become minus 180. Okay. So amplitude ratio is equal to 1 and phase angle become minus 180. When the amplitude ratio is equal to 1, and so whenever you equate your amplitude ratio is equal to 1, and when you calculate the frequency corresponding to that, that is called gain crossover frequency. And whenever the phase angle is minus 180, in fact, minus 180, which is phase lag, that's why this minus comes in. Okay, then you compute the frequency response corresponding to that. That is called phase crossover frequency. Okay, so now this is the following is the body stability criteria. So in body stability criteria, I'll just read out. So consider an open loop transfer function, okay, which is, so it has to be strictly proper, which that is first check we'll have to do. The number of poles should be more than zeros and has no pole located to the right of the imaginary axis. So this you will be able to identify very quickly. So another point is the open loop frequency response should have a single critical frequency, a single crossover frequency, which essentially means that you should not have frequencies, multiple frequencies in which it would become minus 180 or amplitude ratio become 1. So it should have only a single frequency, which either the frequency should be monotonically decreasing or increasing, so that at two particular frequencies you cannot have the amplitude ratio is equal to 1 or phase angle becomes sorry about that. Okay, so now just a second. Yeah. So the idea is the amplitude ratio as the crossover frequency WC, which is the crossover frequency corresponding to the phase, should be less than 1. So that is the way you would be able to identify whether the system is stable or what. So you would now it's become very clear to you, should be very clear to you that there is no problem of time delay here because you don't have to do any character. So because this would also be applicable for every system that containing time delay. So now let's look at it graphically how it looks like. So so based on this what you call this stability, so how much you are away from the stability, how much you are safe from the unstable region, how much you are safe in the stability region. This is characterized by two parameters called gain margin and phase margin. So how to calculate the gain margin? So gain margin is calculated when if you have the phase. So whenever your the frequency at which your at basically the frequency at which the phase angle to the minus 180, which is called a crossover frequency, you project back because it's body stability. So you are expected to have a body plot with you with the top plot representing amplitude ratio versus frequency, bottom plot representing phase angle versus frequency. So when the phase angle become minus and 180, you project it up. Okay. Then it would cut at certain frequency here. You see. So this is the minus 180. You project either cut here. It would all be same because this is log and other one is semi log. So this axis are exactly the same. So whenever you get at this point, this is the gain crossover, sorry, phase crossover frequency, and again you project back to the x-axis of the amplitude curve. So the inverse of that is called the gain margin. So you will get what is known as the critical amplitude ratio. The inverse of that would be the gain margin, which essentially showcases how far or how safe you are from the stability from the amplitude perspective. Now look at from the phase perspective. When the amplitude ratio is equal to 1, okay, you project the that perpendicular down, it would cut at the amplitude graph as well as the phase graph. So, and the frequency at which it cuts, it's called the gain frequency, phase over frequency. See? So the point that you cut the phase angle and you project it on the what you call the y-axis, that's called phi g. Okay, the phase margin is the difference between this phi g and minus 180. So phi g minus 180 would be the phase margin, which would be 180 plus phi g. So how far you are away from the phase instability. So gain margin, as I told, it is the inverse of the critical amplitude ratio, which is evaluated at the critical frequency WC, which is the gain WC, which is the phase crossover frequency. So border stability criteria said ARC should be less than 1, or gain margin, which is the inverse of ARC, which should be greater than 1. So yeah, so how far you are stable from the gain side and well as the phase side. So this would give you some perspective. So phase margin, in fact, it means how much additional time delay you can be included to make it. So how much additional time delay can be accommodated to make the system unstable, because it is 180 plus 5G, right? So so how much time delay you can accommodate would be computed by that. So now we will just see one aspect how this is used in computing the controller design. So I'm saying just look at the case when you are looking at only at the proportional control, because see, you have your Ziegler-Nichols and Tyrus-Leuben and all things ready, so everything there, the table is essentially based on the fact that you do the field experiment based on the proportional controller. So let's keep the proportion, assuming that you have the proportional controller installed in the system. So we have to get the KCU, which is the largest value of the gain that results in the stable closed loop system. So the open loop transfer function should contain 1 plus Kc times G, because there is nothing else there. So AR into when you convert into the frequency domain, it would be so the in fact, when you compute the amplitude ratio, so Kc would stand because it's a constant, and it is the gain margin, or the amplitude ratio corresponding to the G. So ARW is the amplitude ratio of G. Okay, at the stability limit, which W is equal to WC, this should be equal to 1. Then, so this is the critical stability. Okay, so this will become 1. Okay, and what is the value of Kc corresponding to that would be 1 by ARG of WC. So at the critical frequency, this is the maximum gain amplitude ratio you can find, and based on that you will get the value of Kc. And phase angle, if it is phase angle, it would be theta W. The phase margin also provides what you call relative instability. So once you have KCU, so you will be able to use many of the controller design methods which was presented in the previous chapters to compute the what you controller details. Okay, so similar to so this is how to do the controller synthesis based on the gain margin. Similarly, we can also look at in terms of phase margin, because they are the margins, right? So your controller should be stabilizable. So you should be moving away from the region of instability. So how far that margin you can have is what you need to look on. So look at theta max is the additional time delay that can be included. Okay. So the phase margin is theta W, right? So basically that phase angle for the phase angle is for the time delay is theta W. This we have computed here. You see? Right here. So we can accommodate that much of extra time delay minus theta W. Okay, so let's check how to do it. So theta max. Okay, so this is the delta additional time delay that you can think of, delta theta max. Okay, omega g, and omega g. So converting this into the degrees from radians, it would be 180 per 180 by pi. So this is the approximate. So for a given phase margin, so you can eventually compute what is the extra time delay that you can accommodate. So theta max is equal to Pm by Wg times pi by 180. And this, so you should be able to tolerate this much time delay technically without making your system unstable. So if for a phase margin so for a given phase margin. So what? So the what you call the heuristic says that for a well-tuned controller, it's good to have a phase margin of 1.724, which essentially means uh, the ARC should be inverse of that. Okay, and the phase margin, which is basically your 180 plus 5G, should be between 30 to 45 at least. So this is the thumb rules that you would be able to use the frequency domain. So there are various other ways also to do it, but I think this is one of the ways to look at controller design based on frequency response, and one of the simplest way to of looking at the controller design based on the frequency response. So with this, I think we'll close the topics and kindly look at the textbook, some problems, and we'll also solve the similar problems in the class. Thank you.